Thank you so much. That was a fascinating presentation, and you did a really good job of making what can sometimes be a very sort of technical and hard to access topic. I thought you did a great job of making it understandable to even me. Felt like I sort of understood what was going on. So thank you so much. That was a really good presentation. There's been so many good questions coming in actually. So I think I'm just gonna launch straight into some of the questions people have been putting to you. So just a quick question before we get into some of the more deeper ones. Path asks. So what actual frequencies of light do you usually use in optical chips? I know you said you can sort of use a range by multiplexing them, but is it sort of always down the sort of red end, the infrared end? Because in my mind, when I'm imagining fiber optic cables, I always imagine like a red laser flashing through them. But is that true, or what do you tend to use?
So in the communications field, we typically use infrared light. Fiber optic, they could actually handle all the wavelengths. I mean, because it's glass, right? So all the wavelengths go through. Only the point is the sweet spot, the lowest optical loss is actually at the infrared wavelengths. And more specific, 1550 nanometer and 1310 nanometers are very specific wavelengths that are very often used. For long haul communications, it's 1500 nanometers. In chips, in silicon, in chips, we have to comply with that, right? Because if we make a transmitter for fiber optics, we need to have the same wavelength, obviously. You can, by the way, see that. You can literally see that in silicon chips, because if light has to go through a silicon waveguide, where the silicon is actually being the waveguide, I mean, if you actually see a silicon wafer, you can see it. If you can see it, that means it's not transparent. So that means we cannot use red laser light because it doesn't go to silicon. However, and most of what I have been showing, it's all in the infrared. One exception is the whole quantum field. Because in quantum field, where you have to interact with an ion, for example, there are very specific transitions. They're typically invisible. And then people are working on photonic integrated circuits in the visible light. And you can do that with, let's say, glass-based, typically silicon nitride in silicon oxide-based photonic integrated circuits. So you can do visible. You can even do you can also do, by the way, long wave infrared, right? You can even do UV a little bit, but most of it, what I've been presenting is telecom wavelengths, which is infrared.
Fascinating, thank you. Bharat asks, how do optical chips work at a storage level? And so remember on one of your slides, you talked about magneto-optical storage as a way it was working. Just as a side note, because I always have to try and get some Royal Institution history in here. Of course, the magneto-optical effect was discovered at the Royal Institution by Michael Faraday in 1845, where he successfully managed to pass polarized light through a very heavy, optically dense bit of glass and was able to rotate the plane of that polarized light. So it's really nice that we've got that link with work that's still going on today. But I don't know if you could say a little bit more about magneto-optical storage, because I sort of feel like this is kind of an old technology. Like, is a mini discs magneto-optical storage or writable CDs? Is that also magneto-optical storage, or is that something slightly different?
Yeah. So if we talk about, let's first talk about storage of light. That has always been a huge major bottleneck, and that's one of the main reasons there are no optical computers. Because storing light is basically impossible because it flies around with speed of light. The best way to store light is to send it into an optical fiber and just keep it there. So basically, if you want to store light, you want to basically transfer that energy or that information into something else. And magneto-optics is one way how that can do it. That's actually relatively new technology. I'll get back to that. When we normally talk about optical storage, it is basically like a CD. Actually, I mean, I'm now sitting in Eindhoven. The CD is invented here in Eindhoven, right? Not actually the university, but Philips, okay? I think Philips, that's one of the few exceptions where the companies have a better scientific track record than the neighboring university. Philips Research Lab was, of course, great. I still think our university is great, but Philips Research Lab is outstanding, right? They invented the CD. That is not optical storage in the sense that the light is not stored, but the light is used to actually write a little grating, so to say. So a little, they change something in the material and they basically read it out optically. So there's still Actually, the information is not transferred so much. It's not that optical light is stored, but it's written optically and it's read optically. But the storage is just in the physical structure of the CD in that sense. The magneto-optic part, that's actually a new phenomenon that was observed only 10 years ago. And we are now looking whether we can actually do that, because the promise is that if we look at hard disks, for example, which are now written electronically, if we would be able to write that all optically, that would go far faster and with far lower energy. We already use optics in hard disks. In the very latest generation of hard disks, we still write it electronically, but we assist it with a little optical pulse to quickly heat up the material. That's formerly called hammer technology, heat-assisted magnetic writing. So we heat it up very quickly with a very short, tiny optical pulse, and then write it electronically. So it's photonics assisted. But if we could do it photonics completely, that would be great. But that's not possible yet.
Excellent. It's also goes on to this question from Nick, where he says, you read an article in the May 27th issue of Nature talking about nanocrystal structures exhibited superfluorescence. So he was just linking that with the idea of could you use superfluorescence to, say, generate light in photonic integrated circuits? Or is it more likely to just come from a sort of laser pulse or other things?
Yes, you can. So you can actually, you can inject, actually, the underlying technology won the Nobel Prize, I think, 15 years ago or so for what we call a frequency comp. So a lot of what I've been talking about, because it's the most easy to understand, are linear processes. So light coming in, going through, red light coming out as red light. We have something what we call nonlinear processes. In nonlinear processes, the frequency of light can change. And in some materials, it can happen. For example, if you have a very short pulse might have a very high peak power. High power changes something in the material. It triggers nonlinearities. So that means all kinds of other photons are generated at different frequencies. And if the peak power of these pulses is high enough, and if all kinds of other conditions are correct, then that means that an optical pulse, which might have a small bandwidth, so only a few frequencies, at the output of the waveguide, after this nonlinear interaction, it can be superluminescence on the order of 1 octave. So an octave is a factor of 2 in frequency change. So you can actually, in the visible, also on a photonic integrated circuit, you can basically make white light out of a single color of laser.
Well, I've just checked this chat and there's loads more great questions, so I'm going to try and get through as many as I can in the next 10 minutes. There's a great question from Steve here, which is what I was thinking as well, so well done, Steve, where Steve says, if the speed of light is the limit for photonics maximum speed, is there room for improvement, like a kind of Moore's law of photonics, or like with, once you get to a certain size of atom, that's sort of the hard limit on transistors? Have you calculated sort of the maximum possible speed of integrated circuits? Is there a sort of theoretical number of transistors or theoretical power limit that you might get to?
Yeah, I think it's so when we talk about speed, it's always a little bit confusing because we have the speed of light, the speed with which a pulse travels around the world and travels around the chip. So there's just the physical speed that it has. But quite often in communication, we talk about the speed that is basically referring to the bandwidth. So then we say, okay, are we talking megabits per second or gigabits per second or terabits per second? So those are two different things. So the speed of light, of course, influences the latency. If we communicate now, we cannot not do that instantaneously, right? Because we actually have to go through a physical distance. But at the same time, there's nothing limiting us to send. At this stage, I can send you 1 bit of information, and it will take you. A finite amount of time before it reaches you. But again, at the same time, I can send you, a terabit or a petabit. I can send you whatever I want. They just all travel in parallel all the way there. So the speed of light by itself, that is more something that has an impact on latency. But the speed of light, as we know it, 3 × 10⁸ meters per second square, does not influence bandwidth. It influences latency, but not bandwidth. And of course, you decrease latency by keeping everything very close together. And now back to the advantage of photonic integration. It's a chip, so everything is close.
Excellent. Toby asks, sort of in the future, when you've sort of solved lots of these problems, do you think it will be possible to completely eliminate electrical components from a printed circuit board or a chip or like a whole, desktop laptop that I'm talking to you on now? Or obviously you'll need to have electricity coming in from somewhere, but to what extent do you think you can eliminate electrical components in a sort of perfect photonic computer of the future?
Yeah. So, I mean, well, you already said it so yourself, you cannot eliminate it completely. I mean, you have to keep one thing in mind. Photonics is not optics. Photonics is part of the field what we also sometimes call electro-optics or optoelectronics, right? There is an electronic component. I mean, a laser that we use is a laser diode. And a laser diode, obviously, is an electronic component. I mean, I'm in electrical engineering, and some of my colleagues sometimes say, what are photonics people doing in electrical engineering? And I often say, I think I do more research on electronic components. I made them, I measured them, I simulated them, and you didn't, because you just download a SPICE model, right? We basically work on electronic components where, photonics comes out. That also means you need to be electronically powered, etc. Okay, but that's the practical side of things. Photonics is not going to replace electronics for the stuff that is now being done. Digital computing will always have a place, and there's no way how photonics can replace a transistor. The photonics is bound by the wavelength of light. We cannot make a well, it would be a very large challenge. We cannot easily replace a 2 nanometer transistor. We have a problem with footprint then. Also, there's a lot of boring stuff that has to happen. There's no need to do all this fancy stuff. A lot of the things I've been showing here is mostly we look at alternative paradigms, but they are there for a specific function. Some of them I've showed, working with big data sets, training for artificial intelligence, but at the same time, if I now want to change the volume on my computer, I mean, all the things that are happening there, I mean, there's not a photonic neural network that needs to do that, right? It's just old-fashioned electronics. And memory, by the way, I already touched on that. Photonic memory as such is also a no-go. So I think it's very important to see, yes, there are some paradigms, some computing paradigms where photonics can do its own thing. But when we talk about mainstream computing, it's about, yes, replacing the communication, the transport, but it's about things going together, the synergy.
There's a couple of questions here about manufacturing, and basically saying there's a current chip shortage, as I'm sure you're very well aware, and anyone who's tried to buy a PlayStation 5 will be very aware of. Do you think focusing on the production of optical chips might help that? Do you envisage sort of in the future they might be easier to scale for certain jobs, like you were saying, for neural networks and so forth? And then Furman also asks, what are the challenges in chip-to-chip communication that are hindering the kind of mass production of this communication? What are the kind of things that are kind of stopping this appearing in our homes and universities and wherever?
So the first question is, does this help? No, because basically the same technology, right? I mean, the TSMCs of this world, they make also photonic chips. Global foundries, etc., they all make photonic chips. But it doesn't help anything because it's a different technology. By the way, in terms of volume, it's far, far, far lower. So no, it's not helping anything in that. However, and now we come to an important part. I mean, there is a reason why we have chip shortage. That's because we haven't been paying attention, especially, okay, now I make a political statement, but especially as Europe, right? Because we basically lost the semiconductor industry. It went to Asia and to the United States. I compared Moore's law with Moore's law for photonics, right? We are 40 years behind. I mean, whether we can extrapolate that, that's always room for debate. But, visionary countries would extrapolate this. So they would think that, let's anticipate that this will also become important. And if we don't do that, then in 20, 30 years, we would have the same issue that we now have with chips that we cannot get it in Europe, for example. Luckily, that is changed a little bit. And Europe as a continent, specifically the Netherlands as a country, I must say, we are very aware that this has so much potential, and it's an exponential technology. Yeah, that's the same thing as just maybe a nice comparison as Corona. In Corona, if you are a few days too late with your measures, you might already be behind, and you might not be able to sort of contain the pandemic. That's the same here. I mean, it's a train. If you jump off the train and you want to get on later, you might not be able to do that. That's the problem with exponential technologies. But I'm very happy to be in the Netherlands, where our government is actually quite aware of that. So, no, and Europe too, by the way. So we don't want to make the same mistakes we did for electronics.
Good point. I've just got, there's loads of questions, but I'll just leave you with.
There was a second question that I forgot to answer, but that was, what was the other one?
It's about what would be the bottlenecks in sort of mass producing optical chips.
Okay, yeah, well, there's I can be very quick. In terms of some technologies, silicon compatible, there is no bottleneck because you can make it in the big foundries. If you look at the more exotic technologies, the bottleneck is that we still need to mature it a little bit.
And just a final question, which I thought was kind of interesting. This might be a simple no, but I thought it was interesting. I know with quantum computing and qubits, that not only is a kind of new technology, but it's also a new way of computing. Like it require different kinds of programming and different kinds of languages. With photonic chips, will they sort of need their own kind of programming language, or will actually programming optical chips be just sort of exactly the same as conventional computer science and use the same programming languages that we use now?
I think it's a very good point. And I do think this is currently limiting progress. Computing, I mean, whatever new computing paradigm you come up with, you're up against existing computers. Existing computers, silicon transistors, the manufacturing of that, and all the computer scientists and computer engineers that have been trained to do something with that, including all the software that's currently running. That is the most advanced technology humanity has ever created, without any doubt. So if you're going to go up against that, you have to come up with some world-shattering new paradigm. Okay, we actually have that. That's not a problem. But you should then still make it happen. And what you need to make happen is that all these different abstraction levels, from the materials to the devices, to the circuits, to the architectures, all the way up to the software and the applications, that you eventually get all the people on the same page. And that is actually one of my personal, and actually I'm actually the scientific director of this new institute. This would be one of my main missions, to gather the people within our university or outside there, and to have them communicate, talk, and ideally get roadmaps there, because my background is photonic integration. We are stars in chips, but someone needs to tell us what is important to make, right? Because we can do 1,001 things, but we would love to hear the 1 or 2 things that are the most important and that make the most impact. And we do not necessarily know that. We are experts in the hardware, not in software.
So that's a really great point and a nice one to end on. So just before I say goodbye to everyone, I'd just like to thank everyone in the chat for all the fantastic questions. Sorry, I couldn't quite get to all of them, but there's lots of really interesting discussion going on. Just a quick reminder to people out there that membership of the Royal Institution is open to absolutely everyone. You can join a fellowship that includes me. Albert Einstein was a member. I'm just trying to think if we had any famous Dutch members actually. I should have researched this, but I'm sure there must have been. But yes, you're dating all the way back to Faraday and other people. And yeah, there's no nomination, no qualification. You just want to like science, like to support our work, and you can sign up. And also, if you've enjoyed the talk, you can also make a donation to the Royal Institution via the link in the chat. So that's all for you to look forward to. Just before we go, Martijn, just anything else that you'd like people to know? If people want to find out more, where can they find you on the internet? And where would you recommend in Eindhoven if people want to go for a city break?
Okay, there's a few questions. I actually put, I'm not sharing my screen anymore, right? But
yeah.
I mean, we have this new institute, the Eindhoven Hendrik Casimir Institute. That would be, we just kicked it off last Monday, right? So this Monday, a few days ago. So not everything's up and running yet, but that would be an entry point. And I think very clearly, I mean, I work in academia, so whatever we do is public. So my name, if you just Google, I think I have a unique name, to be honest. It's very Dutch and very, rather unique. We're not a big country. If you just Google my name, you get to my university page in Eindhoven, you get to my LinkedIn page. I'm always happy to connect with people on LinkedIn to answer some questions. Actually, that would be one of the best ways, connect to LinkedIn. That is best for a personal contact.
Fantastic. Well, thanks very much, Martijn, and just thank you to the Embassy of the Kingdom of the Netherlands here in London for organising this event with us. And it's just as I say, it's just always really nice to be able to reflect the sort of international nature of science and be able to chat to people all over the globe about fascinating research that's going on. So just remains for me to say thank you so much, Martijn, for a fantastic presentation, and we'll see you all again soon. Good night.
Okay, thank you.